So this is the last video about sound waves and Doppler effect. So a few problems. So again, here we have a question about standing waves. So when you are playing music, any instrument, when you are using any instrument, you're gonna have a mix of standing waves. So like, for example, if you are playing guitar, it's a mix of standing waves. Let me show you if I have an example there. So here, for example, so the timbre, what makes a guitar, that will be the weight placed on each standing wave. So that will be the fundamental, the second harmonics, which is also the first overtone, second overtone, and so forth and so on. And each standing waves, when you're gonna add them, they have a different weight. Okay, so the amplitude will be different. But the pitch that we hear, so the frequency we hear, will be only given by the fundamental. So any music, when we listen to it, it's gonna be mixed of all the standing waves, but with different weight on them. Okay, so which harmonics we are adding with which amplitude will give the quality of the tone, or it's also called the timbre. But we're gonna hear only the frequency of the fundamental. Okay, so I don't know if you have, so that's a good example there. So for example, if you have a violin, for example, I'm not sure what's the frequency here, but we're gonna hear this frequency, even though all those overtones will be here. And the amplitude depends how much of the harmonics is in that sound here that you are playing. Okay, so anyway, let's go to the problem here. So here you have 3 harmonics, right? So that will be the fundamental, the first, second harmonic or first overtone, third harmonic or second overtone. And here you are adding the first and the second, and here you are adding the first, the second, and the third with different weight, different amplitude for each one. So here you just want to know if you understand what's going on here. So which completes its cycle in the least amount of time? Is it the first, the second, or the third? Least amount of time. So one cycle, so this is one cycle. The time for one cycle is the period. So the third harmonic will have the smaller period or the larger frequency. So the answer is the third harmonics, right? At the second position where the 3 curves intersect, the curves are all, so they intersect here, and the second point they intersect there. Okay, so it means it's a node for the 3 of them. Okay, and then if the frequency of the first harmonic is 100 Hertz, what is the period of the second harmonic? So between the first and the second, you see that this is half a wavelength for the first harmonic, and the second harmonic is just one wavelength. So it means the frequency between this one and that one has been multiplied by 2. Okay, so the frequency has been multiplied by 2. So the frequency here is 100 Hertz. So the second harmonic will be 200 Hertz. So the period will be 1 over 200, which is 0.005 second. Okay, so 0.05 0.005, right, second. Okay, and then they say, okay, for this one you add the 3 harmonics. So which one do you think will show the relative amplitude of the harmonics? So if you look at the first one, so this is the first harmonics, and you look at that one. So this one is the first and the second. So first is there, and it has a large amplitude because we find this. But the second harmonic here, you see, you have it here, it's very small. So the second harmonic should be smaller than the first one. And then you add the third one, which is large also. Not as large maybe than the first one, but larger than the second one. So we want a small second one. So small second one, A or C. So the best answer, second harmonic is the smallest, so the best answer will be C. Okay, so you can pause the video and check that on your own. So if you have a fourth harmonic, you don't know what will be its amplitude, right? The amplitude we don't know. Because again, if you look at the guitar here, you see fourth harmonic could be a smaller amplitude and the fifth harmonic will be a larger amplitude, so we don't know. But what we know is that the frequency will be higher. Okay, as you increase the harmonic number, then you increase the frequency. And if you combine everything here, if you combine everything like this, you notice that's going to be 0 here, that's going to be 0, and here it's going to be 0. So the period here is the same as the first harmonic. So even though you keep adding harmonics here, you keep the same frequency. That's a frequency we hear. So the pitch will be, or the frequency will be, the same as the first harmonic, or the period will be the same as the first harmonic period. Okay, so even though you keep adding harmonics, you keep the period the same as your first one, the period of the first harmonic. That's how it works. Okay, so this is about the Doppler effect. So Doppler effect again. Here, you see if, for example, you have a source and an observer. So there is an apparent shift in frequency if the source or the observer is moving relative to each other. So as this one is moving toward that, you decrease the wavelength, you increase the frequency. If it's moving away from that, which is the observer, you see you increase the wavelength, decrease the frequency. Okay, so there is a relative motion between the weather balloon and the station. So here, the weather balloon is moving away. So this is the source. The source is moving away from the observer. Now, if you have a different balloon and you want to have the same shift in frequency, so if the balloon is moving away at 600, so the station has to move at 300 toward the balloon. So the relative speed will be 300. So we'll get the same shift in frequency. So you can pause the video. And the balloon is moving away. So if the balloon is moving away, the distance between the wavefront will increase, right? So if it's like this one, doesn't matter if it's the observer moving or the source moving, if they are moving relative to each other, apart, they are moving apart, the distance here will increase. So this here, I will have a larger distance. So it will increase. So the answer is C. So here it says why the percentage change in frequency much greater when the weather balloon transmits sound wave instead of radio wave, because you can have also radio Doppler shift for light. So how come it's easier to detect for a sound wave and not for radio waves, for example? So the relative shift in wavelength, okay, depends on the speed of the observer or the source relative to the speed of sound. The speed of sound is 340 meters per second, so it's not that hard to detect it. But if you have for light, so the speed of the source and the speed of light is 3 times 2 to the 8. So usually this is really, really big, so that will be equals to 0 unless the speed is very close to the speed of light. So it's easier to detect for sound. So the answer is A. So in that case, if they are traveling side to side, so it means they are not moving relative to each other because they have the same speed. So there is no apparent shift in frequency. So the answer will be A. So what's happening here with light? If a galaxy is moving toward us, so the wavelength will be smaller, so it's going to be blue shifted. If the galaxy is moving away from us, the wavelength will be larger, so it's going to be red shifted. So if this is in the lab and we measure that, see the wavelength here is smaller. Wavelength is smaller, so it means it's blue shifted, so the galaxy is moving toward Earth, right? So again, if it's moving toward, you see those, the wavelength gets smaller. Wavelength gets smaller, it's relative to each other, they're getting closer to each other. Okay, and this one is about, it's about standing waves again with a standing wave with a clarinet, something like this, right? So it's closed at one end, and here you have the equation for the frequency and or for the wavelength here, right? So you're gonna have so sometimes here you should pause the video. You see you have two equations with two unknown, but you can look at the multiple choices here. It makes things easier. So you have L, which is unknown, okay, equals N. For example, one of the wavelength is 8 and then 4. So that's going to be 2N equals L. So N could be 1 or 3 or 5 or 7. So let's take a guess. If N equals 1, so L equals 2, but this is not there. If N equals 3, so 6, this is here. See, and then 5, so I have 10, and it's not there. So the only answer is C. Okay, so n equals 3. That means lambda equals 8 meters. Right? Let's say now L equals 6. So 6 equals n over 4 times 4.8. Let's look at the other n. So 6 equals n times, so that would be 1.2. So n equals 6 divided by 1.2, which is 5. It's 5. So this is for n equals 3, and this is for n equals 5. So you see lambda gets smaller and the frequency gets larger. Okay, so you could, you don't have to use this one. You can use that one to check, but to go faster, you can just use this one. Okay, and this one is what? So here they just want you to check, they're just checking if you know your equation. Okay, so the equation is lambda. So they talk about what is the wavelength. So you have a wavelength times frequency equals the speed, which is 3 times 10 to the 7. Okay, so lambda will be 3 times 10 to the 7 over 1.09 times 10 to the 9, which is about 3 times 10 to the negative 2. It could not be 3.3, so it should be smaller than 3 or 3. So which is meters, so it will be about 3 centimeters. Okay, it cannot be 3.3. So that will be the only answers that make sense, which is A. Okay, next one. Next one here. I wonder if we are missing one equation here. So anyway, so this is the definition for decibel. And okay, so you want to, so the pen threshold for pen is 120 decibel. So we have 120 equals 10 log in base 10, and you want to find I, the intensity of threshold of pain. So cross this one, so you have 12 equals log in base 10 I over I sub 0, which is that equals 10 to the 12. So I equals 10 to the 12. I sub 0 is given here. So 10 to the negative 12, which is 10 to the 0 watt per meter square. So the answer is B. Okay. So if now it's got something is going up and then it stop. It stop and then it's coming back. So when it's moving, it's I think the question was if you launch something in the air that emits a sound. So it's gonna slow down, stop, and then it's coming towards you. So it means the shift in frequency, it's gonna fall to 0, and then it's gonna increase again, right? It goes to 0 because it stopped moving, and then it's gonna increase again. So the answer is A. So it's something you launch in the air that makes noise. So first it's moving away from you, but it's slow down, stop, and then it's coming back. So the answer is A. That's it.